Well, how are you doing, learners? I hope you are doing well. I would like to take this opportunity and welcome you in today's lessons as we are going to discuss about mid-latitude cyclones. But before I start discussing today's lesson, I would just like to take this opportunity and encourage you to subscribe into my YouTube channel. Then let's discuss today's lesson, which is mid-latitude cyclone. This is the first topic under the section of climate and weather in grade 12. What is it that we are going to discuss today in this lesson? What is it that we are going to look and discuss today in this lesson? Firstly, we are going to discuss about origin of low and high pressure cells, especially low pressure cells. The reason behind that is because, remember, mid-latitude cyclones that we are going to discuss today are low pressure systems. So it's key to understand low pressure cells. Then secondly, we are going to discuss about low pressure cell, thirdly, high pressure cell, mid-latitude cyclones. Well, we will also discuss the general characteristics of mid-latitude cyclones, the conditions that are necessary for the formation of mid-latitude cyclone. Then we're also going to discuss about the stages in the formation of mid-latitude cyclone. Remember, we have 4 stages that we are going to discuss of mid-latitude cyclone. Then firstly, let's discuss about the origin of low and high pressure cells. They originate due to the differences in the way the land and water masses heat or cool at different latitudes. That's why we have low pressure cells and high pressure cells. This then causes high and low pressure belts to break up into pressure cells. It can be pressure cells of high pressure cells or low pressure cells. Pressure cells are generally represented by circular isobars on synoptic weather maps. Remember, the isobars, they indicate the atmospheric pressure. So the pressure cells are generally represented by the circular isobars on synoptic weather maps. Then let's start by looking at low pressure cell. Low pressure cell, what you need to understand is they're associated with warm temperatures. When we have warm air, because it's light, warm air rises. Because it's light, warm air rises. As you can see in this diagram, we have what? We have warm air that rises or that is ascending. Low pressure cells, they are associated with warm rising air, generally in summer. Then if you can just have a look at this diagram, you can see as we have warm air that is rising. Then air in low pressure cell is converging. Convergence occurs in a low pressure cell. How do you identify a low pressure cell? It's key to understand that. You can identify a low pressure cell by letter L in the center. You can identify it by letter L in the center, or you can also identify it by the lowest pressure. The lowest pressure in a low pressure cell is found in the center. In the center of the low pressure cell, that's whereby we have what? We have the lowest pressure. Air moves in a clockwise direction in the southern hemisphere in low pressure cells. In the southern hemisphere, air moves in a clockwise direction in the southern hemisphere. Then in the northern hemisphere, air moves in an anti-clockwise direction. Then your low pressure cell is associated with unstable weather conditions. And now let's discuss about high pressure cells. High pressure cells, they're associated with cold air, because cold air is dense, it's heavy, it descends. It descends because it's heavy and it's cold. As you can see from this diagram, in a high pressure cell, we have descending air. Then your high pressure cell is associated with cold, subsiding air, generally in winter. Then divergence occurs in a high pressure cell. Then how can you identify a high pressure cell? You can identify a high pressure cell by the letter H is found in the center of the high pressure cell. And then also the highest pressure, as you can have a look at this diagram, the highest pressure is found in the center of a high pressure cell. That's whereby the highest pressure is recorded in the center. Direction of air movement is anti-clockwise in a high pressure cell in the southern hemisphere, and then is clockwise in the northern hemisphere. High pressure cells are associated with calm, clear, and stable weather conditions. Then now we can discuss mid-latitude cyclone. Mid-latitude cyclones, remember, they originate when warm tropical westerly winds meet the cold polar easterly winds from 90 degrees north and south. Where do they meet? They meet at the polar front. Then the polar front occurs at 60 degrees north and south latitude. That's whereby the mid-latitude cyclone originates. They originate when we have the tropical westerly winds, which are from 30 degrees north and south. They meet at the polar front. The polar front is at the latitude of 60 degrees north and south. That's whereby the westerly winds and the polar easterly winds meet. And that's whereby the mid-latitude cyclone originates. If you can just have a look at this diagram, you can see from this diagram we have the westerlies. The westerlies, they are from 30 degrees, latitude of 30 degrees south, as you can see in this one. We have latitude of 30 degrees there. Then we have the westerly winds. They meet at the polar front. This is the polar front at the latitude of 60 degrees. They meet with the what? With the polar easterlies. The polar easterlies are from 90 degrees south. And then that's whereby it meets at the polar front. It's key to understand where they originate. Then mid-latitude cyclones, they have alternate names. They're also known as temperate cyclones, frontal depression, and extratropical cyclones. Now let us look at the general characteristics of mid-latitude cyclones. Since we have discussed where they originate, now let us look at the general characteristics of mid-latitude cyclones. They occur between the 30 degrees to 60 degrees latitudes. Their direction of movement, how do they move? They move from west to east. They move from west to east, or we can say eastwards. Why do they move from west to east? Remember, they are steered by the westerlies in the westerly wind belt, which means the westerlies, which means the mid-latitude cyclone are driven by the westerlies. So because they are driven by the westerlies, or they are steered by the westerlies, that is why their direction of movement, they move from west to east. That is why in our country, they affect the southwest coast of South Africa. Temperate cyclones, they consist of fronts. We are going to discuss about the fronts, about their formation as well. They can also be identified by the fronts. They have warm front and cold front. The size of mid-latitude cyclones. Mid-latitude cyclones, they are very large cyclones because they have a diameter of about 1,000 kilometers. So you can see that they are very large cyclones. Can you imagine a diameter of about 1,000 kilometers? They occur throughout the year, but they affect South Africa mainly in winter, especially the southwest coast of South Africa. Then they last for about 4 to 14 days. Those are the characteristics of mid-latitude cyclones. It's key to know where they originate, their movements, and other general characteristics. Now let us look at the conditions that are necessary. Now we are going to discuss about the conditions that are necessary for the formation of mid-latitude cyclones. The conditions necessary for the formation of mid-latitude cyclones. Firstly, warm subtropical air from 30 degrees north and south meets the cold polar air. The cold polar air is from latitude 90 degrees south. Where does it meet? At the polar front, which is at latitude of 60 degrees. Both air masses move parallel to each other in opposite direction. Why? Because of the presence of Coralis Force, which causes the air masses to deflect. Then frictional drag between the air masses causes them to interact with each other. This frictional drag occurs as a result of, number one, difference in the speed at which both air masses move. Because we have both the air masses have different speed, then there is the frictional drag that occurs. Secondly, because of the uneven surface over which they move. And then number three, because of the temperature differences between land and sea surfaces. That is why we have this frictional drag. It occurs because of these 3 points, valid points. Then now let us look at the stages. We are going to discuss the stages in the formation of mid-latitude cyclones. We refer to the stages of the mid-latitude cyclone as cyclogenesis. The term cyclogenesis, it refers to the various stages of development of mid-latitude cyclones. We have 4 stages. Firstly, we have the initial stage. Secondly, we have the development stage, which we also refer to it as wave formation stage. And thirdly, we have the mature stage. And lastly, we have the occlusion stage. We are going to discuss each and every stage in details. Let's start with the initial stage. With the initial stage, we have warm tropical air from 30 degrees south and cold polar air from 90 degrees south. And then the warm tropical air from 30 degrees south and the cold polar air from 90 degrees south. It meets or converges at the polar front. Remember, the polar front is at the latitude of 60 degrees. Then the polar front is at the latitude of 60 degrees south. Then we have the warm tropical air and the cold polar air from 90 degrees south. It meets or it converges at the polar front. And then remember, we have the presence of Coralis Force. The presence of Coralis Force, it causes both air masses to deflect. In the southern hemisphere, it causes air masses to deflect towards the left. That is why, if you can have a look at this diagram, we have the warm air, that flows parallel with the cold air. Remember, the cold air is from 90 degrees south. Then you have the warm air from 30 degrees south. It flows parallel at the polar front. What causes it to flow parallel like this? It is because of the presence of Coralis Force, which causes to deflect, which causes both air masses to deflect. That is the initial stage. As you can see from the diagram, we have the cold air that flows parallel to the warm air. Where does this happen? It happens at the polar front. Then the second stage, which we refer to it as development stage, or we can say is the wave formation stage. The wave formation stage occurs when the frictional drag takes place between the two air masses, between the tropical air and the cold polar air. When there is this frictional drag that takes place between the two air masses, then we have the development stage. Then a wedge of warm air begins to be uplifted by the cold air. You see, in this stage, if you can just have a look, this is the development stage. We have warm air, we have cold air. Because of the frictional drag, the warm air, as you can see, it begins to be uplifted in the development stage. Then the fronts begins to form as air converges in a clockwise direction in the southern hemisphere towards the low pressure center. As you can see in the wave stage or the development stage, the fronts, they begin to form. But the fronts at this stage, they are not well developed and they are not clearly visible at this stage as they begin to form. Then what follows next is the third stage. This stage is the matured stage. This stage is the matured stage. At this stage, the wave deepens or intensifies, and isobars at the front kink and point away from the low pressure. The cold front and the warm front and the sectors are fully developed in a well-formed V shape. If you can have a look at this diagram, this is the mature stage. Now we can clearly see the cold front. This is the cold front. And we can also clearly see the warm front. Then we have the cold front. What do we have behind the cold front? We have the cold air. Remember, the cold front is the leading edge of the cold air. That is why behind the cold front, we have cold air. And then we can also clearly see the warm front. Behind the warm front, what do we have? We have the warm air. The warm front, it is the leading edge of warm air. That is why behind the warm front, we have warm air. This is the sector of warm air. We also refer to it as warm sector. And then here we have the sector of cold air, which we refer to it as the cold sector. Then in the mature stage, we can clearly see that the cold front, the warm front is clearly visible. We can see the cold sector and the warm sector. And both the fronts, they have formed what? A V shape. they have a V, they formed a V shape, which is the cold front and the warm front have formed a V shape in this stage, which is the matured stage. Cooling, condensation, cloud formation, and rain are associated with the rising air. Remember, as the cold front and the warm front, warm air is uplifted. The cold front forces the warm air to be uplifted. Then when we have warm air that is being uplifted, cooling, condensation, cloud formation, and rain are associated with the rising air. And then we have the last stage, which we refer to it as the occlusion stage. This stage is reached when we have the cold front, when the cold front catches up with the warm front. That's whereby we have what? We have occlusion stage. We have occlusion stage when the cold front catches up with the warm front. Remember, the cold front moves fast and catches up with the warm front. Occlusion starts at the apex. What is the apex? Or why does it start at the apex? Remember, the apex, it is the shortest distance between the two fronts. Just have a look at this diagram. If you can just have a look at this diagram, we have the cold front, we have the warm front. Occlusion starts at the apex. This is the apex. That's whereby we have the shortest distance between the two fronts. That's whereby the cold front catches up with the warm front at the apex. We can have a cold front occlusion. We can also have a warm front occlusion. It's very key to know and understand what's happening in the cold front occlusion and the warm front occlusion. A cold front occlusion takes place when the coldest air is found behind the cold front. And this causes the warm air to be uplifted along the cold front. Which means when we have, as the cold front catches up with the warm front, and then we are going to have the occluded front. When we have the cold air is found behind the cold occluded front, then we refer to that one as cold front occlusion. And then this causes the warm air to be uplifted along the cold front. And then we can also have a warm front occlusion. A warm front occlusion takes place when the coldest air is found ahead the warm front. So in other words, when the cold front catches up with the warm front, and then when we have the warm front occlusion is when the coldest air is found ahead the warm front. So those are the stages of mid-latitude cyclone. But I will also go back and discuss the mature stage. We are also going to look at the cross-section of the mature stage of mid-latitude cyclone. As you can see, this is the mature stage. This diagram shows the mature stage of a mid-latitude cyclone. Then in this cross-section, this is a cross-section of a mid-latitude cyclone in the matured stage. You can see as we have the cold front. Behind the cold front, we have what? We have the cold sector, whereby we get cold A. And then we also have what? We have the warm front. Then behind the warm front, we get the warm sector, whereby we have warm A. And then a cold front leads the cold air in the cold sector. And then the cold air moves under the warm air ahead of it, and upliftment occurs, which means the warm air is uplifted as the cold air moves under the warm air. Then the warm front leads the warm sector. Warm air rises above the cooler air ahead of it, and upliftment occurs. The warm air is uplifted. Then both fronts, which is the cold front, is associated with upliftment, cooling, condensation, and cloud formation as well. At the cold front, as you can see, the cold front, rapid upliftment occurs. Then it leads to cumulonimbus clouds formation. As you can see here, we have cumulonimbus clouds. They are formed here along the cold front. And then at warm front, more gently upliftment occurs. And then we have what? We have broadband of stratus and nimbostratus clouds will be formed along the warm front. Then what else you need to understand is that the cold front is associated with high amount of or heavy rains. And then your warm front is associated with light showers, as you can see from this diagram. As you can see again, in this diagram again, the cross section of a mid-latitude cyclone. As you can see, we have the cold front leading the cold air behind. Then we have the cumulonimbus clouds, then associated with what? With heavy showers. We have the warm sector there. Then we have the stratus clouds. Then the warm front is associated with moderate to light showers. Well, learners, I hope you understood the lesson. I will end here for today's lesson. Please don't forget to subscribe to my YouTube channel.